Today we are going to study Science and Technology Part 1st. Chapter 1 Gravitation. Newton's Universal Law of Gravitation. In the last video, we had already studied what is gravitation. We also studied the three laws given by Kepler on planetary motion. In fact, Kepler obtained these laws simply from the study of position of planets obtained by regular observation. He had no explanation why the planets actually obeyed these laws. So, now we are going to see how these laws help Newton in formulation of his theory of gravitation. Now, let's suppose you are holding two balls in your hand. Consider these two objects with mass m1 and m2 kept at distance d from each other. Take a look at figure 1.5, which shows the gravitational force between two objects indicated by F, and the mass of the two objects are m1 and m2, which are separated by distance d. This distance is measured between the centers of these two objects. Now, mathematically, the gravitational force of attraction between these two bodies can be written as F is directly proportional to m1 m2 upon d square, or F is equal to g m1 m2 upon d square. Here g is the constant of proportionality and it is called as universal gravitational constant. The SI unit of g is Newton meter square per kg square. In SI unit, the value of g is 6.673 into 10 raised to minus 11 Newton meter square per kg square. Friends, this value of g is a constant term and is very important for numerical calculations. So, do learn it by heart. Uniform circular motion or magnitude of centripetal force. Now consider an object is moving in circle with constant speed. If m is the mass of the object and v is its speed and r is the radius of circle, then it is shown that the force is equal to F is equal to mv square upon r. Thus, if a planet is moving around the sun in circular orbit in uniform circular motion, then the centripetal force acting on the planet towards sun must be F is equal to mv square upon r, where m is the mass of the planet, v is its speed and r is the distance from the sun to the planet. Now, the speed of the planet can be expressed in the terms of the period of revolution t as follows. The distance travelled of the planet in one revolution is equal to perimeter of the orbit 2pr, where r is the distance of the planet from the sun and t as in pi. Now, the time taken is equal to period of revolution is equal to t. We know speed is equal to distance upon time. Thus, v is equal to distance travelled upon time taken. As distance travelled is equal to 2 pi r and time taken is t, therefore v is equal to 2 pi r by t. We had already obtained that F is equal to mv square upon r. Thus, substituting the value of v in the formulae, we get F is equal to m into 2 pi r by t bracket square upon r, which is equal to m pi square r into 4 upon 2 square. Multiplying and dividing by r square, we get F is equal to 4m pi square upon r square into r cube by t square. According to Kepler's third law, t square upon r cube equal to k. Therefore, F is equal to 4m pi square upon r square into k. But 4m pi square upon k is equal to constant. As k is constant, 4 is a constant number, value of mass, that is m, is constant for that particular body, and value of pi is also a constant. Thus, 4m pi square upon k becomes constant. Therefore, F is equal to constant into 1 upon r square. Therefore, F is directly proportional to 1 upon r square. Thus, Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for the circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified this force with the force of gravity, hence postulated the inverse square law of gravitation, stating that the centripetal force is inversely proportional to the distance between the bodies. Earth's gravitational acceleration. According to Newton's second law of motion, when a force is acting on a body, it is in acceleration. Thus, the gravitational force due to the earth on the body results in its acceleration. This is called acceleration due to gravity and is denoted by small g. Acceleration is a vector quantity, as the gravitational force on any object due to earth is directed towards the center of the earth. The direction of acceleration due to gravity is also directed towards the center of the earth, that is vertically downward. So, as the acceleration is dependent on the direction, it becomes a vector quantity. Value of g on the surface of the earth. We calculate the value of g using Newton's universal law of gravitation for an object of mass m situated at distance r from the center of the earth. The law of gravitation gives F is equal to g into capital M into small m upon r square, where capital M is the mass of the earth. Previously, we considered two bodies as in mass m1 and m2, where formula was F is equal to gm1 m2 upon r square. But we always consider the mass of earth by indicating capital M. We also know that force is equal to mass into acceleration. Therefore, F is equal to small m into small g. From the two equations 3 and 4, we get mg is equal to gm m upon r square. Thus, small g is equal to capital G into capital M upon r square. Now, we are going to calculate the value of g on the surface of earth. So, the value of small r is equal to capital R, which is the radius of earth. Thus, the value of g on the surface of the earth is small g is equal to capital G into capital M upon capital R square. Now, we know value of capital G is 6.67 into 10 raised to minus 11. Value of capital M, that is mass of earth, is 6 into 10 raised to 24. And value of the radius of earth is 6.4 into 10 raised to 6. Thus, substituting these values, we get value of G equal to 9.77 meter per second square. Thus, the value of G on the surface of earth is 9.77 meter per second square. This acceleration depends only on the mass and radius of the earth. So, the acceleration due to gravity at a given point on the earth is same for all objects. It does not depend on the properties of the object. Hence, same amount of acceleration is exerted on every object on the earth's surface. Variation in value of G. We had already studied that value of G is constant anywhere on the surface of earth. Now, does this value changes as in change in height or depth, or is there any change on the surface of the earth which causes change in the value of G? So, let's study change along the surface of earth. As the shape of the earth is not exactly spherical, so the value of G vary along the surface of earth, and so the distance of point on the surface of earth from its center differs somewhat from the place to place. The earth's radius is largest at equator and smallest at the poles. Thus, the value of G is highest at the poles and decreases slowly with decreasing latitude. Thus, it is lowest at the equator. At the poles, the value of G is about 9.832 meter per second square, and at the equator it is lowest of about 9.78 meter per second square. Change with height. As we go above the Earth's surface, the value of R increases and the value of G decreases. However, the decrease is rather small for heights, which are small in comparison to the Earth's radius. For example, remember that the radius of the Earth is 6400 km. If an airplane is flying at height 10 km above the surface of the Earth, its distance from the Earth's surface changes from 6400 km to 6410 km, and the change in the value of G due to it is negligible. But remember, the value of G decreases with increase in height, as G is inversely proportional to radius. Here are some typical heights and values of G at those heights are given in the following table. Place height in kilometer and value of G in meter per second square. On the surface of the Earth, on an average, on the surface of the Earth, height is 0. Value of G is 9.8. At Mount Everest, height is about 8.8 km. Value of G changes, but the change is negligible, so it is considered as 9.8 meter per second square. Next, maximum height reached by man-made balloon is about 36.6 km. Thus, the value of G changes to 9.77 meter per second square. Then, height of typical weather satellite is about 400 km, and the value of G reduces to 8.7 meter per second square. Height of communication satellite is largest, about 35700 km. The value of G decreases considerably to about 0.225 meter per second square. Change with depth. The value of G also changes if we go inside the Earth. The value of R in the equation G is equal to Gmm upon R square decreases, and one would think that the value of G should increase as per formula. However, the part of the Earth which contributes towards the gravitational force felt by the object also decreases, which means the value of m to be used in the equation G is equal to capital G into capital M upon R square also decreases. As a combined result in change in R and capital M, the value of G decreases as we go deep inside the Earth. It goes on decreasing considerably as we go deeper and deeper inside the Earth. The value of G is about 0 at the center of the Earth. Mass. Mass is the amount of matter present in an object. It is actually the composition of the matter in the body. The SI unit of mass is kg. Mass is a scalar quantity as it does not depend on any direction. Its value is same everywhere. Its value does not change even when we go to another planet. According to Newton's first law, it is the measure of the inertia of an object. Higher the mass, higher is the inertia. Weight. The weight of an object is defined as the force with which the earth attracts the object. The force of an object of mass m on the surface of the earth can be written by using equation W is equal to F is equal to mg, where small g is equal to capital G into capital M upon capital R square. We usually tend to be confused between mass and weight. The main significant difference between mass is that it is the composition of the matter in an object, while weight is the force with which the body is attracted towards the earth. The weight being the force is a vector quantity as it depends on the direction. Its SI unit is Newton. The value of mass remains same throughout the universe. Even when we go on other planet, the value of mass will be same. But this isn't the case for weight. The value of weight changes from place to place, as the value of G is not same everywhere, though its mass remains constant everywhere. Here are few practice questions. Do answer these questions. If you have any doubt regarding this chapter, do ask in the comment section below. Do subscribe my channel and click the bell icon for notification. Do like and share the video. Thank you.